Hey guys, how are you doing today? This is Terrence. Welcome to the 7th episode of Rhino Python and GhPython Playground. The pattern we are working on today is this pattern, is this wavy and bumpy surface, but with hard edges. This pattern is actually referenced from Zaha Hadid's installation, The Common Ground, which launched in the Venice Architecture Biennial in 2012. Oh, let me bring up this page. It is this project, this shiny structure. I will put this link in the introduction of this video so you guys can click the link, go to this page and enjoy this structure. I was deeply attracted by such kind of structure that constructed by the soft curves, while it poses a strong sense of existence. So in the rest time of this video, we will work together to find out the mechanism behind this pattern, and we will apply this pattern to our surface. So let's get started. Now let's take a look at this pattern. It's quite straightforward. It's not as complicated as some of our previous works. It's actually an implementation of the lattice pattern. But what makes this pattern different is the architect actually created the second layer of the lattice pattern over the first layer of lattice strips. And also, the second layer of these strips slightly moves away from the surface, which makes the surface look bumpy and provide a sense of depth. So let's draw some sketches in our sketchbook to try to explain what we should do to create this pattern. So first, I want to draw some curves to represent our target surface. It might not be perfect, but I think clear enough. Yeah. Then I will draw the first layer of lattice strips, like this. And I will draw one more. I'm not going to do them all. That's a waste of time. We just need to make things clear. Then, we can regard this first layer of curves as the skeletons of our pattern. Then we need to create some twin curves between this major layer of strip. There's gonna be our twin curves like this. And also, we still need to draw some twin curves between each pair of the lattice strip. Each pair of our major lattice strip. Sorry. Do it here as well. And as you can think about, some part of the points on the second layer of lattice pattern should move outward from the surface. And let me draw a section. This is gonna be the section. Let me draw a section of this surface. And some points on the second layer of the lattice strip still remaining on the surface, while some of them slightly moved outward from the surface like this. And now when we connecting these points, or we can say we can interpolating these points, we will create this bumpy pattern or bumpy section. And we can regard these yellow lines as our muscles of this pattern. Then we just need to pair all of these curves, pair them each other, loft them to create the surface, to create the new surface or to create our target surface. We just need to pair them one by one or pair them with each other. We can call this part as our skins. So these three elements will help us to create this pattern. It's not hard. The real hard part is the manipulation of the points on this surface. Now let's draw a simple let's draw a simple sketch to explain how we should create and manipulate those points. And as usual, we should first divide this surface vertically divided into some how to say divide, just divide it vertically. Then we need to divide each of these curves. But something different is on the in every other line of curve, our point distribution is slightly swift from its previous line of points. And the distance of the swift is equals to, so first let's take this as P1, let's take this as P2, let's take this as P3. The distance between these points could be, we can write pseudocode here. We can say this is distance between P1 and P2, while in its later layer of points, we need to shift distance equals to this. We need to shift half of distance away from its previous line or its previous list of points. And after we create this kind of point layout, we can find a way to connect different points, then create these wavy curves or these lattice curves. And it is still kind of abstract, but I think we can achieve this in our code. So let's go back to our code editor. At first, we need to create a surface, create our target surface. What I use is this kind of mushroom column shape, and you guys can use whatever shape you like, just to make sure the shape should be an untrimmed surface. If you put in a trimmed surface, they will cause a lot of problems that no one can solve that. So just make sure the input shape should be untrimmed. Then we can create a Python script node here, remove all the inputs, right-click, show code input, and input is path. Then we will add a file path node here, right-click, select our Python file. We also need to synchronize it. Let me do it again. New file location. Oh, sorry. This one. Yes. And I will create a panel to check if these two nodes are successfully connected. I can print go here, save the code. Okay, the code shows up here. That means these two parts are successfully connected. Then I will also create several more inputs to input some values that could be very necessary for creating the pattern. The first one is the surface. I will use a surface node to put this shape into our Python node. And I will hide the original one to make things less chaotic. And then I will create an input called uNumber, which represents how many that represents how many divisions we want to have along the U domain of the surface. And also I will create a vNumber as well to represent how many points we want to create along the V domain of the surface. This could be much larger, this could be a 12. Then inside our code, I want to make sure these two inputs are integers. If they are floats, there will be some problems. So I want to say vNumber equals to integer. Oh, sorry, it's uNumber. uNumber equals to integer uNumber, and the vNumber equals to an integer of vNumber as well. Then I can print out these two numbers to check if they are successfully converted. Save the code. Yeah, you can see these two values now appearing here, and they are integers. Another thing I want to do is to make sure these two numbers will not be too small. Like if we slide this U number to 0, that will definitely cause a lot of problems. So I want to say if the U number is smaller than maybe 4, then we will fix the U number as 4. And we will do the same thing on the we will do the same thing on the U number. Oh, okay. V number smaller than 4, we can fix the V number as 4. Then we can save this. And I think the next thing I want to do is I want to check if this surface is successfully input to our Python node. I will say print. Sorry, my throat is a little bit dry today. Print surface, then we will see a line of number, a line of combination of number and the characters. That means the G that represents the GUID of our target surface. So this is just GUID. When we print it out, we will know this surface is successfully input into this Python node. Then I want to create a function called divide. Define a function called divide surface with 3 inputs: the surface, the U number, and V number we just created. Then inside this function, I want to first find out the U domain and V domain of our target surface. The function we are going to use is U domain equals to rs dot surface domain, and with the first input is our surface, the second input is 0 or 1. The 0 represents the U direction, while the 1 represents the V direction. We do the same thing here, surface domain, with input surface and direction as 1 in this time. And then we want to find out the steps along the U domain. We already have the number here. We want to divide the surface into 6 pieces along the U domain. So we need to find out the step of each pieces. We can say U step equals to U domain and minus U domain start divided by the U number. This should be a lowercase here. Save it, and let's call the function here to check if this function is properly written. U number and V number as well. Save it. No errors here. That means the function is successfully executed. Then we need to loop over the U number for I in range U number and try to create the horizontal lines according to different steps. Then I think the function we need to use is rs.extract extract iso curve with maybe 3 inputs. The first one is the surface, the second one is the domain. Sorry, I don't know why this part is not working. Sorry, there was some problem with my Visual Studio Code, and I restarted it. Now I think everything goes back to normal. And let's keep working on this shape. The function I'm going to use is called rs.extract isocurve with 3 input. The first one is the surface, the second one is gonna be a parameter, which is the UV coordinate on the surface. The coordinate is the U domain start value multiply, start value multiply, it's the U domain's start value plus I multiplied by U step. Then the V value could be 0. And the third input is the direction, is which direction of the isocurve we want to extract. And this time we want the curve, the isocurve on the V direction, because we are subdividing the U direction, we want to V curves. This sounds a little bit weird, but you can tweak these values, then you will figure out what's going on here. And it returns a list of isocurves, and what we need is just the first one. Then we can, I can add an empty list called curves up here. Then we can just append the newly created curve to our empty list base curve. It's kind of a debugging append base curve, yes. And at the end, we should return the curves. Save it, and you can see these green lines. These are our subdivisions along the U direction. It's our vertically subdivision. And I noticed that there is one more curve missing here. That's because we need to add the U number with 1 in the loop. Now you can see we have all these vertically distributed curves, vertically distributed subdivision curves. And the next step is to divide each of the curve according to our U number, or according to our V number, V number or V subdivisions. So this time we need to create a new function called divide curve, CRV. What we need is the input curve, the V number, and I think we might also need a direction to figure out which curve we are locating on, because the curve with the plural index is different. The subdivision on the the subdivision on the curve with plural index is different from the subdivision on the curve with the singular curve with a singular index. Well, it's a little bit messed up. So let's working on this function. We can say PTS equals to an empty list used to contain all our going to be created points. Then we need to find out the length of our target curve. We can use the function rs.curveLength. CRV is our input curve, because we want to divide the curve with equal length. So we need to first calculate the total length, then divide the length with the V number. So this is our next step. We can say length step equals to a float value with curve length divided by a V number. Then if the direction equals to 0, that means if the curve's index is a plural value like 0, 2, 4, 6, or for 6, 8, this kind of value, such value modulo by 2 equals to 0. If this kind of value provided, our points equals to rs dot divide curve length with 2 inputs, the curve and the length step divided by 3. So please take care of here. The length step divided by 3 is intended to keep subdividing this part into 3 equally distanced parts. So I want to divide by 3 here to create the major point for to create points for the major curve and the subcurve simultaneously. And else, if the direction is not equals to 0, this will be quite complicated. First, we need to create some temp points equals to rs dot divide curve length curve, but here we should set length step divided by 6. It's actually length step divided by 3, then divided by 2. We combine these two as divided by 6 because we want to have a half distance shift in every other curves. Then we need to create a new start point for the curve with index 1, 3, 5, or something like that. The function we are going to use is curve closest point with 2 inputs, the curve, the temp points PTS with index of 0. That means our first point inside these temporary points. Then we will also need our new end as rs dot curve closest points with curve and temp PTS with index of, sorry, this should be the second point, not first point. The second point, then there is a small distance between the first point and second point. The small distance is something we need to trim out, is something we need to discard. So the new end should be the second last point that can help us to trim the curve in both ends. Then we will create a new curve with the function rs.trimCurve. Also 3 inputs. The first one is curve, the second one is our domains we just created, the new start, new end, and the final input is you can see here by default the third input is true, but actually this part of code functions differently in RhinoPython and GhPython, so here we should keep this false. Okay, I think now we have our newly created curve. We just need to do the same thing as this line. And then we will have our target points. I think we can just return points here to check if these points are successfully generated. And let me create a new empty list here. I can say points equals to an empty list. Then I just want to check if this point is successfully generated. So I will add another output here called B, and PTS. I can say test points equals to an empty list here, and I will append the newly created points. Oh, sorry. return points. I will put all these newly created points into this test point list. It is test pts no, it should be pts dot. Sorry, let me think about how to write this. Test pts dot plus, sorry, test pts plus equals to our new function divide curve with the curve v number and the index modulo by 2. Index modulo by 2. Yeah, let's try it. Save the code. Global name curve is not defined in line 8. Oh, sorry, there's a syntax error here. Base curve. And I think a equals to this. Curves and test pts will also return these test points. Now you can see we have this, and if we slightly increase the number of U subdivision, we will find here there will be a half distance shift between every other line of subdivisions. And I think we finished the first step of our pattern, that is generate a multiple list of points for us to create our curves. And now, as we have all the points here, what we need to do next is to organize these points. We want to organize these points according to the curves, the index of the curve they are locating on. So here we will create a new empty dictionary called points dictionary equals to an empty dictionary. We already talked about the dictionary structure in our previous videos, and also you can just Google search what is a Python dictionary. You will get a deep understanding of this kind of data structure. Then we need to remove this temporarily created test points variable. I think I should remove it here. Replace it with the pts dictionary with the key I equals to the divide curve. And remove these test points. Remove this B. Save it. See, there's no error, and also we remove all the points from our outputs. And here I want to print the dictionary to see is this dictionary successfully stored all the points we just created. I can say pts dictionary dot items. I think it's this one. No, not items, keys. Oh yes, here it is. Now you can see we have our 0 to 10 list of points. And this last value is corresponded to our U number. So I think we successfully created this point dictionary. Let me make a double check. Let me say 0. The first part of the dictionary to check is length. To check if this dictionary included all the points we just created. Here will be 36 points. This value is corresponded to this value multiplied by 3 as we did here. So I think our point dictionary is functioning well. Now I can remove this print and print code. And then I think I need to create another function to use the point list, to use the points in the point list to draw the curves we needed. So just up here, I can say draw edge, I can define a new function called, here I can define a new function called draw edges with 3 inputs. The first one is point dictionary, the second one is UNumber, and the third one is the surface. Then inside here, we need to first create an empty list called curves. Then we should loop over each point inside the first part of the dictionary, or the points in the dictionary with the index 1 as our start point. So we can say for I in range length points dictionary with index 0. Then we should come up with some conditions like, so I think I need to bring up my sketchbook again to explain how to organize these point lists. And here is our sketchbook. Let me draw some lines to represent the horizontal lines in our pattern. Okay, and we have points on each lines. These subdivided points with equal distance. The lines with the plural index will have a half distance shift from the previous one, so they look a little bit different in every other lines. And here, like this. Okay, and then we should mark these points with the index 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6. You see the curve, the point list with the plural index, the length of this point list is just 1 unit smaller than the previous one. 3, 4, 5, 6, 7, yeah. 0, 1, 2, 3, 4, 5, 6. Now let's think about how we can connect these points. Let's take a look at a general condition. We can start from 3. The curve we need is like the first one, 3, and back to 1. The second curve is start from 3, back to 2, go to 3, then back to 2 again. The third one is 3, goes to 3, 3, and 3 again. The final curve goes from 3 to 4, back to 3, then back to 4. It is like this. And the next unit take place at the index of 6. That means this pattern take place every 3 times. Let's draw the pattern again, then you can figure out what's going on here. The first one, the second one, the third one, like this. Okay, this is our major condition. So the second part are these in-between curves. It's actually a flip of this major pattern. It starts from 4, go to 4, then go to 4, then 4 again. The 5 is the point with index 5 goes from 5 to 4, back to 5, then go to 4. The point with index of 2 performs the same. While something different is just the first, the list of these first points and the list of these end points. in the first part, we just, sorry, I make this a little bit obstructive. I remove these newly created lines and doing this. At the beginning of the surface, the lines follows this logic. They are all zero. They are the interpolation of the points with the index of 0. And at the end of the surface, it performs like starts from 0, goes back to 6, and 0. Oh, sorry, I think I make a mistake here, but this should be 7 as well. It requires another points because we divide with the same number, with the same number of segments. And the end here is 7, 7, 7 like this, and also we need one more like this. Okay, so this is the logic behind our creation. Let me complete this pattern to make things more clear and reasonable. And to the points here, sorry, this should be a dark red line. Like this. Okay, now you can see we have 3 different conditions. The first one is our most commonly seen condition. It's located in where the index modulo by 3 equals to 0, and it's not starting point, it's not the end point. Then we can draw these blue line patterns. The second condition is these interval points. They draw the former one of interval points follows the same index along the line, while the latter one has 1 digit shift in every other lines. Like this starts from 5, 4, 5, and 4. This part works the same. And the third condition is our AND condition, which take place in these 2 ends, that we will need to write extra code to just create these end curves and lines. Now let's go back to our code and finish this pattern. And I prefer to put this sketchbook aside here to, as a reference of how to build in logic to connect these points. But I want to close these obstructive panels. Okay, put it here. Now we should go back to the line 20, this part, and create our first condition, which is the general condition. We can say if I modulo by 3 equals to 0 and I is not 0, we should make sure it's not start point, and it shouldn't be the end point. Length pt dict with index 0 and -1, I think. Then we should also loop over these 4 points. The first points could be the 3 minus 2, then -1, then -0, then +1. So we can say for j in range, start from -2 or -2 to 2 with step 1. The range is inclusive at the beginning but exclusive at the end, so the -2 is included in the loop. We can see the first step is just 3 minus 2 equals 1, but the last value in this range loop should be just 1 because it's exclusive. It doesn't include this 1. It doesn't include 2. It just goes from -2 to -1 to 0, then to 1. The end part is exclusive, just a small notice. Then we create an empty list we loop over k in range, we loop over all the u numbers, all the u divisions in this pattern. We can say range u number. Also, we should +1 to ensure the last line of points were successfully connected into our curves. And if k modulo by 2 equals to 0, we need to append the point dictionary with a key k and with the index 1. This k represents in which line the point indicates. If the points locates in the first line with the index 0, then we just append the point in the point with the key value 0 with the index 3. Okay, so else we need to append the point dictionary with the key value k, but the index should be I plus j. And this part means this value plus the j. If this j is negative 2, this value is gonna be 3 minus 2 equals 1. It's kind of this logic. Then after this whole loop, we need to create the curve just based on the point we just created. And we can say curves.append rs add interpolate dot add inter curve with 2 inputs, surface and points. Save the code. Let's first check if this first part of code is functioning well. We should return curves, and maybe we need to call the function here, curve append. We can say in range okay, as I think we can do this here. We can say curves plus equals to draw edges with a point dictionary, the u number, and also the surface itself. Now let's check, can we generate curves with this part? Some error here. Let's go back to the line 20. Oh shit, points dictionary, syntax errors. Runtime error, line 55. Yeah, I think we need to do some debuggings here. Let's print the length of points to check, can this successfully generated? Okay, the problem takes place at this part. Dot append rs dot interpolate add the interpolate curve to. Okay, well, I just messed up at the inputs here. Now we can rewrite this line of code and to make things work. Yeah. Now remove this print just for debugging and save it. And you can see we have all our we have all our major stripe patterns. The next thing we want to do is we want to create these strips on the end and the beginning of the surface. So we need to create new statements, create new conditional statement like L if I equals to 0. Then we can say for j in range 0 to 2 and with a step of 1. And we do the same thing as here. We just create new empty list and for k in range u number plus 1. If k modulo by 2 equals to 0 and points dot append points dictionary with the index k and I, else points dot append points dictionary k I plus j, and at last we copy this line of code, paste here, save it, and you can see we just created this starting strips, and these two parts of code are identical. I think if you guys they are just different in the start point and the end point, as we already explained in this sketch. So if you are interested, you can make this part of code as a function to make the code much cleaner. So I'm not gonna to do this. That will make the video looks very chaotic, very hard to understand. So I just keep the code here. But if you are interested, you can find many ways to make this much simpler. Then we will think about the condition at the end of the surface. We can do L if I equals to length points dictionary 0 minus 1, it's gonna be checked if the index equals to the end of the point list with the key value of 1 in the points dictionary. Well, too complicated to explain this, but when you write code, things is gonna be very clear. And for sure, we do the same thing again, range. This time it should be start from -2 and ends with 0. Actually ends with 1, but you know the range is end exclusive, so I just write the ends with 0 here. That means ends with -1. In range and points equals to, no, I don't need to type this. I can just copy this part of code here, paste here, and to make sure a correct indentation. Save the code. Oh, there must be some mistake here. Let me check. Let me tweak these values to check what's going on inside here. Okay, I think I know what's going on here. This is because the last point on the point list is not appended to the whole subdivision points. So we need to add some lines of code here, which let's go back to this divide curve function, and we need to manipulate the point list. First, we need to find the end point on the curve. And with the curve, sorry, my Visual Studio Code starts. My Visual Studio Code has a problem again, so I have to hand type this function. But I think in your end, the function will automatically pops up. And after we find the endpoint on the curve, we can check if the endpoint in our list is corresponded, or is the endpoint in our list is identical to the endpoint of the curve. If not so, we need to append the endpoint to our point list. We can say pts.append endpoint. Save it. Now the curve goes back to its position. And for sure, we can tweak this value to see the results. There's still some weird part in here, but to solve this, that requires many hours of work. That requires use an algorithm called binary search to find the distance. So I think it's not essential in our playground. So if you are interested, I will have a video talk about how to use binary search to find the distance on the curve in the future. Maybe when the video has been made, I think you guys can figure out how to solve these small hiccups. So for now, just don't care about it. And we have all this. The last condition we need to do is to find the curves, these interval curves created by these interval points. And sketch again. The final thing we want to do is these yellow curves, so we don't need to do any condition, we just need to say else. Else, first we should create point list equals to an empty list. Let's loop over the U number. This part is slightly different from this former part. And we can say range U number plus 1. And inside here, if k modulo by 2 equals to 0, we will append the point into the point list, and k and I. If not, we would say points.append points dictionary with the key value k, but the index value is I minus I modulo by 3 minus 1. And this line of computation will help us find the point here. We can say if it is 2, after this computation, it will automatically got 1 in the other point list. So just keep in mind this, or you can just draw some sketches to find the logic behind here. And at the end, we can say curves.append rs dot. I can copy this part and paste it here. Close this one. Let's check. Can this part work? Okay. It functions pretty well. And we have all our curves. The final thing is just to move the points away from the surface. Now let's go back to our main function, the divide surface function. Before doing this, I'd like to add the final input on our GhPython node, which is called the offset distance. Now I want to set it as 3.0. This could be a float value, it's not that strict. Move this away, organize it a little bit. Then let's go back to where? Go back to this part. before assigning these points to the point dictionary, I want to first assign this to the points list equals to this part. Then modify this point dict with the key value I just equals to points. Then I can loop over all the points to modify the points before inserting all the values into this point dictionary. Now let's loop over all the points inside this list. We can say for j in range length points, and if j plus I modulo by 2 multiplied by 2, another computation here, then modulo by 3 is not equals to 0. This helps us find these points which we need to move away from surface. Just a line of computation will save us a lot of time. And we should first calculate the normal on the normal of the surface the normal of the surface on the specific position, on the point's position. We can say normal equals to rs dot brep. Sorry for the bad visual code. It's very obstructive now, but okay, I can hand type this function name. rs dot brep closest point. I should be very careful here with surface points with index j, and what we want to return is the fourth value inside this inside the output of this function. There will be a UV coordinate of the surface. Then we can use this value to find the normal vector on the surface. We can say rs dot unitize normal. Sorry, I made a mistake again. The fourth value is already a vector value. We don't need to find the vector again. It is already a vector value. We just need to normalize the vector, make its length to 1, make its length equals to 1. And if I equals 0 or I equals to u number, the normal vector equals to normal vector x, normal vectors y value, while the z value equals to 0. That means when the points locating on the bottom or the top of the shape, we don't want it have shift on z direction. We just want it move along the xy plane. So this is what we do on this line of code. And then the next step is to scale the function according to the distance we just provided. So we need to add another parameter to this function, or to this divide surface function. At the end of the parenthesis, we add surface offset here, and we can use this value to scale our vector. And here we can say normal equals to rs dot vector scale normal, which is our vector and the offset value. For sure, you can use the random function to modify this value, to tweak this value, but for now we just keep it what it is. And I think the last step is to move the points. Is rs dot move object the point and the move vector, then save it. Oh, something goes wrong in line 94. Oh yeah, we just forget this one. Offset dist. This name should correspond to this name, and save it again. Then you can see now we created these wavy curves. The final thing is we just pair them with each other and loft these curves into surfaces. So here we can say at the end of the code, after we created all the curves, all the points, just at the end, the final step, we can say for I in range. I think to make things clear, I need to modify these names to curves. And here should be curves. This should be surfaces. Okay. And for save, I can say surfaces equals to an empty list. Then let's go back to our root loop. Let's say length curves -1 and the surface. Append the lofted surface. The function is rs.add loft surface with two surfaces as a list. With two curves as a list, sorry. The first curve is the curve with index I. The second curve is the curve with index I +1. Yes, and save it. Now I want to preview off this part and also hide this part. Use a surface node to export all these surfaces. Now you can see we have all the surface we need except the end one. If we want to loft this part, we just need to add another line of code. We can say if rs.is surface, sorry, face closed, LOSED. That means let's check if this surface is a closed surface. If it is, we will need to loft these two lines, the first line and the final line on this pattern. Just only in the condition that this surface is closed. So we will do this. This line of code means we need to check is this surface is closed. The first input is surface, the second input is the direction. If we put 0, we will check if these two sides are closed. And if we put 1, we just check if these two sides are closed. And if this condition is true, our surface can append our final loft surface dot add. I just need to copy this here and paste it, modify the value as 0 and -1, save it, and we fill this gap. So this is the whole process of creating this pattern. I think we have all we want. And that's it for today's video. I think before we end this video, we can also tweak these values to see how we can modify these patterns just by these 3 sliders. This is the offset distance. This is the division along the vertical axis or the z-axis, and this is the division on the surface along the v-domain. Yes, along the v-domain, I think. And also, if we bake this pattern, bake it and hide it, turn to the rendered mode, wow, it looks pretty attractive. And I think you guys can use any kinds of surface you like, and to apply this pattern to that surface, you will get a lot of amazing shapes. So that's it for today. Thank you so much for watching. Please let me know if you have any thoughts or any comments. I will really appreciate you share with me how you think. So that's it. Thank you so much. Bye bye.